All right, good morning, nerds. Today's tutorial, we are going to be working on getting our enemy to use the Nav Mesh, which is a different kind of a concept. This one is we're gonna be spending a lot more time in the editor today than we have in the last couple sessions. This is FPS tutorial 5. So as with some of the previous ones, we want to make sure that you have done FPS 1 through 4 before you get to this point. I did notice just after I click stop on the last tutorial, I have a few lines of code left over. So if you want to go into the enemy script again, I do have a few lines of code. These debug logs are playing every time I shoot, or every time the enemy gets hit. And we really don't need those anymore. They're not really serving a useful purpose. So I'm gonna go ahead and delete those. And again, I should have done that in the last tutorial. I just forgot and hit stop before I got around to deleting those. So those really don't have anything to do with today's tutorial. They have a lot to do with last week's tutorial, but they're a good thing to go ahead and get rid of. Alrighty, so today we're gonna be working on the Nav Mesh. And what the so Nav Mesh is short for navigation mesh. And what it is it's a way to organize pathfinding in a way that's going to help Unity do this relatively efficiently. And if you were to Google pathfinding algorithms or pathfinding code, you're going to find literally dozens and dozens, if not hundreds, of ways to do this. And all of them have varying degrees of efficiency, varying degrees of complexity, and honestly, very, very different usability scenarios. So for example, one of my personal favorites is the A* algorithm, which is written literally A*. And the A* algorithm is fantastic, except for it's really designed for something that's more grid-based. If I were to try to use that system on this first-person shooter, honestly, it wouldn't work very well unless I divided things out into a grid, and the maps are so large, it would get inefficient and clunky and really cumbersome in memory really fast. There's dozens of different ways to do it. Fortunately, the Unity built-in navigation system is actually quite good, especially in a smaller scale game where we don't have a ton of navigational complexity. So it's going to work great for our needs. Now, a couple things to keep in mind before we get started is kind of a sanity check on our maps. Now, if you followed along exactly with my tutorial when we first started this, you're probably already in pretty good shape. But some of the things that are very, very important for this to work is, number one, all of our map objects need to be touching the floor. If they're going through the floor a little bit, that'll be fine. But if they're not touching the floor, you're going to have some problems. So it's okay. It's better to actually go too far through the floor than to not be touching it at all. The other thing that we need to do is we need to make sure that any, I'm going to call these doorways, but any gaps in our wall that we intend for an object to be able to pass through need to be at least, just for safety purposes, you want them to be about at least 3 times bigger than an object. This one here on an eyeball looks to be about 5, and that is my smallest gap in my entire map. So I'm in good shape, but if you have some that are, for instance, maybe like looking more like this, that is just gonna be way too narrow. And even if I widen this out a little bit, you know, that's wider than one of my cylinders is by at least a little bit, but that is still not going to give me enough room to pass through. So this is not going to be a good, this is not going to be good for my pathfinding algorithm. So give yourself some room. And this is way more than enough. This feels right. This is great. The other thing that is some limitations, the pathfinding algorithm does not do well with things like a platformer where there's gaps between parts of my floor. It does okay if there's a staircase and the rest of the level design is similar, but on 2 floors, you can usually get away with that. But you're also going to have some other issues if you are trying to do things like actual doors. Things like that are going to make this pathfinding algorithm not as good as it could be. There's ways to do it, and there's probably some tips and tricks with Nav Mesh that I'm not aware of, but in general, it works best with relatively open terrain like what we have here. Okay, but you can have a lot more walls. Like, it doesn't really matter. You could add tons of walls. You could make it more of a maze. and that pathfinding is still going to work. It's just that you want, fairly good gaps between walls, no overhangs, things like that. So this is going to be pretty good. Okay, having said that, now that we've got some of the basics out of the way, what we need to do is we need to open up the Nav Mesh screen. And the way we do that is we go up to the window menu, and things are going to look a little different for you PC users, but it should be relatively similar. So we're going to go up to the window menu item, we're going to scroll all the way down to UI and click on navigation. What that's going to do is that's going to open an additional panel where the inspector goes. And you could drag this out and move it around, but honestly, it's probably fine right there where it is. And so this is our screen where we start dealing with this. And you may be on one of these other tabs. I've used Object most recently, so that's why it defaults me over there. It doesn't matter because we can look at all three of them. So Nav Mesh is a system that is going to use a thing called agents. And typically our default setting is humanoid. And for purposes of this system, a humanoid is basically anything that traverses ground like a human does. And that's going to be pretty much anything that we're going to create. If you create a monster, even something weird like a caterpillar or a slug or something, that's still going to be technically a humanoid for purposes of collision, for calculating movement, things like that. If we get into things like birds, that might be a little bit different, but this is going to be pretty much for anything that traverses land like a person does. And the defaults, this is what we're using to generate our mesh, but we can also override these on an object-by-object basis. Generally speaking, though, for this, when I'm generating a mesh, I tend to calibrate the mesh for the biggest object I'm working with. In this case, though, it's going to default to the standard cylinder size, which is also identical to the standard capsule size, with a radius of 0.5, a height of 2, and then step height is basically how high can it climb, like on a 90-degree incline, for example, if I'm climbing up stairs, because that's not going to be level, and then how far of a slope can I traverse. And we can adjust these numbers. Maybe my character can't go up very steep, and maybe my character can climb really steep. Once you get over 60%, or 60 degrees rather, it doesn't calculate terribly well. So 45 is a good starting point for that. And it really, for our intents and purposes, it doesn't matter because we've got a flat plane as our map anyways. And we're not doing anything with steps. The other thing that we need to look at, we can actually generate user built-in areas. This is for overriding sections of the mesh. Generally, we don't want to touch this, so we're going to just leave this whole section alone. We'll never go into here in the course of this tutorial, aside from literally right now. Or if I accidentally click. And then we're going to skip over bake for now and jump straight to object. And object is where we define things that should be affected by the mesh. And when we're generating our mesh, we're going to do a thing called baking. One of the challenges with navigation and pathfinding and things like that is all the math that is involved in finding the shortest distance, because anytime we involve distance, it involves the Pythagorean Theorem, which involves a square root, and square roots are disgusting to calculate the math for in real time. We want to avoid square roots like the plague. And so in order to avoid that, what we do here is we do a thing called baking. And what that's going to allow us to do is generate all of the math for it ahead of time, so that if I'm in any given location on the map, Unity has already pre-figured out all the combinations of, if I want to get from here to there, wherever here is and wherever there is, it's going to pre-calculate all of that. And so all it's going to do is basically essentially look at a chart and figure it out from there, rather than doing all this math. And we don't want it to have to do math in this instance. Another place where you're going to see baking is not in this tutorial series, but anytime we talk about lighting, typically to avoid the complexity of calculating lighting, we will bake the lighting ahead of time, and that does all the light bounce calculations and everything ahead of time as much as possible, so that we only have to account for the moving objects. The static objects that aren't going to move anywhere are all pre-calculated. Which is a little out of scope for this tutorial, but I'm just kind of trying to connect some knowledge to some other things. So we've got our basic layout here. This is looking great. The next thing that we need to focus on is getting our mesh actually created. So we need to teach it two things. We need to teach it what the floor is, and we need to teach it what walls are. So I've expanded out. I've been usually keeping this thing kind of packed, but I'm going to unpack my walls so that way I can kind of see them all here. So I'm going to click on my floor, and you're going to notice that over here in the Object tab, my options kind of changed once I selected that. What we're going to do is for every single object that we have that needs to be part of the map that's not moving, we're going to mark it as navigation static. And in the floors case, we're going to say, hey, the floor is something that we can walk on. Our other options would be not walkable and jump. Jump is a little tricky to deal with. That's way outside of the scope of this tutorial. But basically, it allows us to set some pathing for some jumping, for some jump options to allow the NPCs to jump across platforms. We definitely do not want to mess with that here. It's very complicated. And honestly, it's not one that I'm particularly good at. But walkable is good. And then we're going to take all of our walls, and we can actually do this in bulk by highlighting all of them. So I'm going to click on the first one. I'm going to hold down my Shift key and click on the last wall. And now you can see that all 4 of my walls are highlighted. I'm going to click on navigation static. We're going to mark those as not walkable. And now we've taught Unity what our map looks like. We can now go to bake and click bake. And this gives us a last chance to look at our Nav agent and make some adjustments. We can adjust a few different things here. We can even go into advanced and like really get some customizations going here. Again, a lot of this is out of the scope of this tutorial. But what you're going to see here once we've finished baking is my entire map kind of turned blue. And you're going to see around each of my walls these white areas. So the reason for these is the white areas represent areas I can't walk. The blue areas represent areas I can. And the reason for this is if the enemy is able to walk in the white lines, it would actually start passing through those walls. So by defining those white spaces, I can walk anywhere where there's blue. And so as long as there's some blue space there, I can walk on it. Now the challenge can be, and we've already kind of talked about how much space you need to have. If these 2 walls were closer together and this blue was narrower, it is possible for things to get stuck in the pathfinding. And that's why I'm like, make it at least 3 times bigger. That gives you enough room to work with here. This is more like 5 times. This is way more space than I needed. But it's just important to kind of keep an eye on like what are our actual needs here. And now that map is baked. Now the thing about baking is that it is now it is statically defined. It's not going to respond to changes. And so for instance, I'm going to grab this wall and I'm going to move it. And you're going to notice that there's still not a white line around the new location of the wall, and the old white line is still there. That's because the old bake is still in effect, and it will be in effect unless I bake again. Fortunately, everything that was marked static and walkable and not walkable is still marked that way. So if I decided to change my mind and put the wall here, I can just click bake again and it will readjust, but I do have to click bake again. So I'm going to go ahead and put that wall back where it was, click bake again, kind of validate. I'm kind of just looking over the size of the map here and just looking to make sure everything kind of looks like it should. I'm looking for kind of white borders around all my walls, white borders kind of around the edge of the floor so he won't run off the side. This is all looking pretty good. So I don't really see any problems here. This is fine. So I'm happy with all of that. We're going to go ahead and leave this alone now. Whoops. We're going to go ahead and migrate. My mouse isn't working the same way anymore, and I'm not sure why. But that's okay. So we've got all of our navigation working. So this is now Unity is aware of what my map looks like. The next thing I'm going to do is I'm going to grab my enemy and I'm going to place him kind of somewhere where he would have to actually do some work to move. And I'm not sure why my cursor is locked now. My hand is not responding to me. So what we're going to do is my scrolling is weird. I'm not sure exactly. why my grip is not moving around anymore. Okay, so the next thing that we're going to do is we're going to go ahead and move my my object. I'm going to move it somewhere kind of more out of the way. So my idea here is, there we go. So my idea here is I want to actually have to navigate around that wall to get to my player. So now what we're going to do is we need to actually teach the enemy to use the Nav Mesh, which is going to involve a little tiny bit of AI coding. But fortunately for us, in this case, the amount of code is, because Unity is doing most of the work for us, is incredibly minimal. So again, we're going to open up that enemy prefab. We're going to go to our code. Or actually, we're going to, before we go even to our code, we're going to add a component. We're going to add what's called the Nav Agent. So Nav Mesh Agent. And the Nav Mesh Agent has a lot of parameters. For example, speed, angular speed, which is its rotation speed, acceleration, stopping distance, which is important. That's how far away from the object we're allowed to get. Whether or not it has auto braking, some obstacle avoidance information, and some other pathfinding catches. We're going to leave most of this stuff alone, but the other thing that I want to do is, because we're setting all of our other values in enemy script and we're trying to kind of plan around having a designer, I want to have my enemy script driving my Nav Mesh agent rather than having two different places to be entering data. So what we're going to do is we're going to kind of set that up as well. So we're going to go into our enemy script. This is the same script that we set up last week. And we're going to add quite a few variables, but these are hopefully fairly self-explanatory, and they should match what we worked on when we were setting up the player's movement for the first time. So some of the things that we're going to work on, we're going to do public float rot angle for rotation angle, just like we did last time with the player. We're going to do public float speed, just like we did with the player. The new one that we're going to be adding today is public float stopping distance, stop distance. And that's going to be, again, how far away from the player do we stop, and don't try to get any closer. And then two game objects that we're going to need references to are going to be public game object player, which is obviously going to be the player. And we're also going to go public Nav Mesh Agent, and this is a tricky one. So we're going to put in Nav Mesh Agent, capital N, capital M, capital A. We're just going to refer to that as Nav. And this is erroring out, and any of the subsequent code that we do involving this is going to error out. Now here's the deal. There's a lot of ways, and you're going to hear me say this a ton of times over the course of this tutorial series, but there's a lot of ways to fix this problem. For instance, if the challenge is that Nav Mesh Agent is part of a using that we don't already have in our code base. And we could add it if we know what it is. If we know the one that we want, we can add it manually. So I can just add the line of code. For instance, if I do using Unityengine AI, that is going to fix the problem. You're going to see, hey, look, it all works. But let's pretend we don't know how to do. We don't know what library it's in. Okay, now what we're about to do is potentially dangerous because it relies on the idea that there's no ambiguity. If there's two different classes that both have the same name, which is very, very common with things like Vector, for example, there's the Unity one, there's also a C# version, there's a monogame version, and all of them are slightly different and not compatible with each other. So that can potentially cause us some problems. In this case, there is only one Nav Mesh agent, so we're not likely to have problems, but you can right-click on this in the in code. I'm going to right-click on this Nav Mesh agent, and I know it has to do with a using that I don't have, but in this scenario, we're going to pretend I don't know which one. So we can click on the first option here, which is Quick Actions and Refactorings. And if I click on that, it's going to give me several options. Most of these are bad. Or at least bad for us because they aren't going to get us where we want to be. But the two that are good are Unityengine Ai Navmeshagent I can click on that, and this is good for what we would call singletons. If I only ever needed to reference the Nav Mesh agent once, this is a fairly efficient way to do it because it's only going to pull this one chunk of code this one time, and it's not going to load the entire AI library for something that we aren't going to use. In our case, we're going to be making pretty extensive use of this, so this isn't really my preferred option here. This isn't a good way to do this, but it is an option that would work. In some cases, we do that. We often do that with the math library, for instance. I don't want to load in the entire math library just to take a square root. I'm just going to call mathf.square root. But in this case, we're going to go ahead and add the entire AI library. So we're going to go right-click again, Quick Actions and Refactorings. And the first option is using Unityengine.ai. If we click that, it's going to go ahead and add that using up here, which I had typed manually a couple minutes ago. And that's going to solve our problem for us. And that's the most common way that I do that. That way I don't have to memorize all the different, like, which library is that again? As long as you get the thing right down here, that'll work. Okay, now that we have that working, in our start, we need to teach it some stuff. So what we're going to do is we're going to tell the code, hey, we have a speed variable. We want the Nav Mesh agent to use that speed variable. So we're going to say nav.speed equals speed. And we're going to do the same thing with what Nav Mesh Agent calls angular speed, we call rotation speed. So we're going to say nav.angular speed equals rot angle. And then the last one that we're going to worry about is nav.stopping distance. How about that? Let's try that again. Stopping distance equals stop distance. And that's going to allow us to kind of reset some things. The last thing that we need to do is deal with player. Now, because it's a game object, if I save right now, I'm going to go ahead and demonstrate this. If I save right now and I've got my enemy, I could just simply drag player into this box in the enemy script, and it would actually work. That would get us where we need to go. However, the challenge is if I ever instantiate off of a prefab or something else, an instantiated object won't respect what's in the hierarchy. And so basically, for example, if I go into my prefab enemy and I try to drag player in there, it just won't take it. And that's because the prefab can't store that. So what we're going to do instead is we're going to have the enemy hunt for the player. And the nice thing is we only have to do it once, and we can do it by looking for an object with the same tag. Now, this will only work if there is only one. The challenge with find with tag is that it will just stop the first time it finds something, not necessarily ensuring that it's the correct one. We would never use this, for example, to find a specific bullet, because you have a ton of objects flying through the air that are all tagged as bullet. That's going to be tricky. If we had several enemies, we wouldn't do it to find enemies, but we could safely do it with players, with player, as long as there's only one. If we network this game later, this technique won't work. And so what we're going to do here is we're going to say, hey, player, let's make a reference. So we're going to say player is going to equal, and in the game object library, that's a big G, we have a function called find game object with tag. Now you're going to notice that there's quite a few that are very, very similar. It's very important for this step that you find game object with tag, not game objects with tag. We do not want that S in there. The S will return an array of game objects, and even if that array only has one thing in it, it will not give us the result that we want. So we want game object with tag. We're going to do parentheses, and in the tags, we are going to type in player with a capital P. And now the enemy should know where the player is. That's going to be it for this chunk of code. So what we're going to do is we're going to go ahead and just save, and we're just going to validate that these values are getting set. So I'm going to go back into my enemy prefab here. We're going to go to my enemy prefab, and I'm going to set Let's see here. My HP is good. We're going to set a rotation angle. I've been playing around with this quite a bit. A rotation angle of about 100 seems to work pretty good. A speed of about 5 and a stopping distance of 10 seems to feel pretty good. The other thing that we need to do is add Nav Mesh Agent in the inspector. So we're going to grab our own Nav Mesh Agent. We can just grab on the toolbar here and drag it up there, and that should fill it in. And now we have all of our own stuff is in there. And then I'm going to click on my enemy and just make sure that it got some similar settings. And so I'm looking at this. It looks pretty good. It looks like it inherited all that. So I'm pretty happy with my results. Now, you'll notice that that does not match the speed, angular speed, and stopping distance in the Nav Mesh agent. What we're going to be looking for is when we click play for these values to actually change, which would tell us that stop function or that start function is working. And we also want to see that player actually gets filled in by the filled in the inspector. So that's all we're going to test on this pass. And if I click play, you're going to see my speed changed to 5, my angular speed changed to 100, my stopping distance is 10, and my player was detected, all in the enemy script. So this is looking pretty good. Also, my HP got set to 100, which it should have. I think we had that working last time, but I'm just still happy when things work. And you're noticing I'm standing around here for a little bit, and if I go back into scene view, the enemy is still not moving. We're in a good spot now, but we're not quite there. Because the next thing that we need to do is tell the enemy, hey, navigate to the object. And in this case, the thing that we're navigating to is the player. Now, I could put that in start as well. However, that's going to be based on a position. I can't say go find the player, but I can say find the player's position. The challenge is as the player moves, that position is going to move too. So what we need to do is we actually need to have it always seeking the player every single tick, which means that needs to go in update. So in update, fortunately for us, the code is very, very simple. We are going to do a quick sanity check, and this will help us when the player dies eventually. We are going to say we want to double check and make sure that the player actually was found. There is a chance that this function doesn't work correctly, so we're going to do if player is not equal to null. That means if the player exists and we know what it is, then we want to do this. And what we're going to do is we're going to set the destination of the nav agent. So we're going to do nav.setDestination. And we're going to set that destination equal to player.transform.position. And that should do us. And then the other thing I'm going to do, just as a double check, is if the player is null, so I can do else, that's going to be, hey, if the player was null, what should we do? Well, if the player is null, I want to hunt for it again. Maybe it despawned, maybe it just didn't find something correctly the first time. Who knows why it didn't work? But we're going to try again. So I'm going to do Control-C on that line of code. And we're going to come down here and paste it in and just try again. And every tick, we're either going to move towards the player or we're going to try to figure out where the player is. And so hopefully this doesn't stay like this for very much, but it'll help us out. And we'll go ahead and save that and rerun. And what we should see is the enemy coming around the corner. There he is. The enemy's coming around the corner and trying to get to us. He's going to stop about 10 away. So it looks like my nav is working really well. He found a pretty efficient route. Now my challenge is going to be if I come backwards and come over here, you're going to see him kind of spin towards me. But if I get close and I spin towards him, you're going to notice that he's not making any effort whatsoever to turn around. And if I was going to sniper right now, actually I'm gonna, I can easily just sniper him and he's not even going to try to fire back. Not that he can shoot back right now anyways, so that was kind of a cheap shot. But my point is this is going to make the game super trivial because all I've got to do is rush enemies and they're not going to be able to turn around. Now, the reason the enemy can't turn around is because of this stopping distance. The fact that he's stopped means that All of his rotation centered around the fact that he needed to move forward in some direction to hit me, so he had to turn so he could move forward, and that's why he was turning so much. Now that he's close, he's like, oh, I don't need to find him anymore, and so he's not even trying to turn. So what we need to do is we need to write a little bit of code that basically says if I'm inside of his stopping distance, we need to rotate anyways. And this is going to look very, very similar to the code that we wrote for us to rotate, with some ifs and stuff put in there. So what we're going to do here is we're going to go to the update function. We're going to give ourselves a couple lines below the navigation mesh. And I'm going to start adding some comments here just to kind of help us label things. So I'm going to write, for this one, it's going to be navigate towards player. And then this one is going to be if player is close, turn anyway. And so now we're going to try to write some code to allow him to turn. Okay, now this is going to be somewhat complex for, again, a very, very short thing. But the first thing that we're going to do is check and see if our distance is closer than stopping distance. And for this, we do need to use a variation of the Pythagorean Theorem. Now, the problem with the Pythagorean Theorem, and I've mentioned this in previous tutorials, Pythagorean Theorem is great, except it involves us needing the square root. And so, for example, let's say that, my distance is, let's just say 5 one direction. So I'm 5 in the x direction. And let's say that I am 4 in the y direction. Okay, well, what's going to happen here is if we pictured this as a triangle, if I'm moving across 5 and 4 up, that would be, if we use the Pythagorean theorem, we remember that a squared plus b squared, whoops, that's giving me variables, and none of this should be typed. I'm just using this because I don't have another thing to write on. A squared plus b squared equals c squared. And the way we would solve this, if this is my numbers, is 5 is my a and 4 is my b. So it would look something like 5 squared plus 4 squared equals c squared. Again, c would be my distance. Whoops, I definitely did not want that. Okay, so c squared. And our challenge here is that if we start doing the math, squaring is pretty easy. That's going to turn into 25 plus 16 equals c squared. I'm just going to use c2 for that. Equals c squared. Now the challenge here is that once I add these together, so I'm going to just add them on this line. I'm going to get 41 is the total. Now here's the catch, is 41 is c squared, which means my distance, I have to square root both sides. The distance is whatever the square root, it's going to be mathf dot sqrt of 41. And again, I've said this a few times, we don't want to do square roots. And since update happens every single tick, we're going to run into some real trouble here because we're taking the square root of whatever this number is every single time. And that's a dangerous thing. Now, fortunately for us, if we think about what is our goal with this, what we're trying to do is compare to our stopping distance. And so really we're trying to see, is this number less than, and c is 10. We already know, like, that's our stopping distance. If we're trying to look for, is the number less than 10 squared? Then here we go. Actually, and it would really be the square root of 10 squared. Or wait, no, mathematical square root is less than 10. But here's the cool thing, is math works both ways. So instead, if we squared this, instead of checking to see the square root of 41, if we left this as 41 and we just square this number, it's the same problem, only this one involves doing a square and the other way of doing it involves a square root. So really, if we get the square of the distance, we don't need we don't need the square root, and we can just solve this using simple squaring. So that's a really fancy way of saying we want to use the squared distance instead of the regular distance, and then just square our targets. So with that in mind, our actual if statement, we need to generate what is our distance? And so we're going to start off with if. Now our distance in this case, and you're going to notice I use that second set of parentheses here, we're going to generate a vector between us and the player. And then we can take the distance of that vector. So distance between two targets is always that one subtracted from us. So we're subtracting us. So we're going to do player.transform.position minus our transform. Try that again. Minus our transform.position. That is the vector between us and the player. So what we need is the distance of that vector. But again, what if we squared it instead of getting the actual distance? Because then we don't need the square root. Fortunately for us, if we put things in parentheses, Unity is going to assume it's a vector because it's a vector minus another vector, which equals a vector. That's in parentheses. So whatever's in the parentheses must be a vector. So we can do dot and any code that we could do on a vector 3, including this cool function. We have magnitude, but we also have square magnitude. That is going to generate the squared magnitude, which will not require a square root. In our previous example's case, it would give us 41, for example, instead of the square root of 41. We can compare that and say, hey, if that is less than or equal to, now we need the square of stop distance. Now there is a math function that will allow us to do exponents, but it's a little expensive for just doing a simple square. So what we're going to do is just do stop distance times stop distance. And that's going to give us the square. And for readability for people at home, I'm going to just go ahead and put a line break in here. You do not need that line break. I'm just trying to make things easier for you guys to read at home. This should be read as one line. Okay, so the next thing I'm going to do is go ahead and do my parentheses, or my curly braces rather. And now we need to figure out what happens if we are inside of there. Now, what we want to do is we want to find the rotation necessary to go from where we are, whatever direction we're facing, our transform.forward. We want to rotate to the vector between them and us, which is again just them subtracting us. But we also only want to rotate by a certain increment. Just like last time, we don't want to rotate all the way there because that would cause things to snap. And we don't want to snap to those positions. We want to rotate gently towards them. And so we have to use kind of a combination of functions to get there. The first one is we need to figure out what our target rotation is. And that's going to be some vector in between our current forward, the vector directly to them, and something in between. So again, using our vector angles as a direction. Fortunately for us, there's a function that's going to help us with that. So we're going to create a new vector. It's going to be a vector 3 called new rotation, new rot. That rotation is going to be equal to the vector 3 dot rotate towards. That's going to give us a partial vector or a partial rotation vector. And we just need to pass in some parameters. What vector are we starting with? Well, the vector that we're starting with is the current vector that we're facing, which is transform.forward. What vector do we want to target? That is going to be, again, player.transform.forward. Again, I'm going to line break this for you guys. So we're going to do transform.forward minus transform.forward. Or I'm sorry, wait. Player.transform.position minus our transform.position. Sorry, not a forward. Okay, that's the vector between them and us. And then the last things that we need to do here is what is our rotation angle? And if you look at the context help here, it is saying that that angle needs to be in radians. Radians is a measurement of a circle that involves basically if you go around a circle completely, instead of being 360 degrees, it is 2 pi radians. And it has to do with figuring out angle versus circumference. In this case, we don't really need to worry about that, or we can just go straight to the equation for that. And basically the equation is for any angle in degrees, which is how we have things, you can also multiply that by pi over 180, and that's going to give you the same angle in radians. That's our conversion. If we need to convert the other way, we would do 180 over pi. So we're going to take our wrought angle, we're going to multiply that by pi over 180 times mathf dot pi gives us pi divided by 180. And then we're going to go ahead and do our last parameter is going to be how much can we allow that magnitude to change. We don't want the magnitude to change at all, so we're simply going to put a 0 in there. And that is a complete statement. We want to make sure that we get that semicolon at the end of it, and we're good. That was kind of a complicated one, so I'm going to leave that on the screen for just a second before I move on. And this is also a great time to pause if you're struggling. And then we're going to go ahead and move forward. Now we've generated an angle that is the partial angle, or potentially all the way angle, depending on how close we were in the first place. But we actually need to apply it. So we're going to say, and we have to do that using a quaternion function. Fortunately, again, Unity is going to do the heavy lifting for us because quaternions are scary. But we're going to do transform.rotation equals quaternion.lookRotation of new rotation. That will convert that rotation into a quaternion, assign it to our forward rotation, and call it good. And that's really, that was a lot of work there to generate that. That was a lot of crazy math. Fortunately, we only have to do that the one time. We will not have to do this again. We can save that. We can go back to our original code again, or not original code, but our project again. And I'm going to get closer because we want to test and see if that rotation is working. And I'm going to move, and I kind of saw him moving as I was running by, but as I move inside of his range, he is still moving and pointing at me, and that's working out pretty well. So he's staying pretty even with me, and that's feeling pretty good. So we've got our enemy moving on a mesh. If we get far enough away from him, he is chasing us, he is spinning towards us, and if I get close, that spin is still working using our manual overrides there. So this is all pretty great. Now the one catch with the Nav Mesh that we haven't really tested intentionally on my part, but is if I shoot him, everything's fine, except he will kind of tend to drift away just a little bit, and that's a little bit weird. And if I hit him, if I impact against him, he starts doing some pretty weird things on the Nav Mesh. Let's see what there we go. We're going to kind of hug him a little bit. That will often create weird behaviors. This is a little bit tamer than normal, but oftentimes we start seeing, oh, there we go. Like I kind of pushed him out of the way. So he is creating this weird drift now. That has to do with rigid bodies. We'll fix that in a later update, but just kind of for now know that you may end up with some slightly weird behaviors, especially if you hit him in weird spots or something. So just be careful with that. But in general, he works pretty okay. And that's it. That concludes our video for today. What we have accomplished in this one is we have made the enemy work on the Nav Mesh, and he is correctly spinning when we get too close. So this is a pretty good amount of progress for us. In our next installment, we will try to get the enemy able to shoot back at us. And once we can shoot back at us and we're able to take damage, a lot of this is going to be copy pasted, but we'll basically be done with the core functionality of this game and we can start moving into some polish. So I'm pretty excited about that. So that'll be for our next installment. I hope you enjoyed this. If you liked what you saw or you found it helpful, please like and subscribe. And as always, keep on creating. We'll see you next time for another adventure.